In this segment, we're going to talk about a technique which will allow us to calculate exactly the volume of a figure that is intricate like this one. Now, we're actually finding the volume of glass that composes this little candle holder. And it turns out that we can find the volume either with or without the candle included. Well, the technique involves the basic technique for a definite integral. And let's talk about that a little bit. Remember that when we talked about integration and definite integration particularly, we interpret that idea as the area under a curve. And we talk about the area between the graph of a function, the x-axis, and within a certain interval. And we talked about the concept of that as being one where we first take little bitty rectangles, and if we add the sum of the areas of a bunch of rectangles along here, then we approximate the area, and then we talk about the limit of a sum and so on. Well, we're going to apply that same idea to volume. Now, let's begin the discussion of volume like this. Now, I'm just taking a very simple type of figure and a predictable type of figure like a cylinder, and we know that to calculate the volume of this cylinder, the formula is pi times radius squared times height, so pi r squared h. Now, I want you to notice this, though, about the formula, that it is the area of the base times the height. Now, in order for us to apply our integration technique to this, what we're going to do is we're going to position our cylinder in a particular way along our coordinate plane. That is, we're going to take it and we're going to just twist it a little bit and position it like this. Now, notice that the x-axis is going right through the middle of it, and I might even position, just for convenience, the y-axis going through, right about here. Then I'm defining an interval from 0 to whatever point this might be, you see, to the spot where it comes out. Okay, so that's the idea. Now, the concept is that we're going to just think about the sum of a bunch of little volumes, and it's the volumes of little disks, hence the idea of disk method. But if we just kind of take a cross-section like this, and the thickness is kind of arbitrary at this point for this disk. So if I just make a cut through this rascal and think about that, and if I twisted it toward you and blew it up a little bit, it would kind of look like this. It would just be a circle, and it has some thickness to it, though, so we can think of it as a little bitty cylinder, you see. And so the volume is pi r squared times the width of this. See, we're thinking about little widths now, and it's the idea that we're applying the same concept that we did before, that we're going to find the volume of many such little disks, you see, and then we're going to narrow them, and the limit of the sum idea will give us the overall volume. All right, so that's the basic idea. Now, notice the notation here, big R squared, for the radius of this. And when we talk about a little volume, a little delta volume here for the little disk, it's pi r squared times some delta x, some x interval, you see, over which we are slicing these little pieces of our cylinder. The overall volume is the limit of a sum, you see, of this expression, and it's just been rearranged to accommodate the situation. Now notice the delta, the thickness is approaching 0 here in this limit idea. This radius is associated with an x subscript I, if we're kind of counting the intervals, you see, along our cylinder and the delta x business. Well, all of that leads us to integration, and the volume then is the integral from a to b, the integral within an interval, you see, of the r of x squared, and that's this part, and then the delta x is the dx. The pi as a constant comes to the outside. And all we have to do then is apply the idea to a specific problem. Let's take a look at one. Suppose we have f of x as the square root of sine x. replace x with 1 everywhere we see it. We've got a 1 here, and then we've got a 1 here. 1 cubed is 1. So this is 2 times 1/3. Oh, that's minus 2/3. And a 1 here gives us minus 1/5. And then minus, let's see, negative 1 in place of x, and so on. So it's pretty arithmetic from here. And then we just collect as we normally would. We find the volume to be 16/15 pi for this figure. In the previous two examples, the solids were truly solid. That is, they didn't have any holes in it. Suppose, though, we drill a hole in the solid. We can still make the calculations we're talking about. Now, here's what I mean. Imagine that we have this cylinder, and let's say that we drill a hole through it from one circular surface to the other circular surface, right through the middle. What kind of thing do we have when we slice it and look at a cross-section? Well, we have a figure that looks like this. It looks like a washer. Now realize what this is. This is a cross-section of that cylinder. So the cylinder would kind of come out this way and kind of go through the board, and we're just slicing it, and here's the cross-section. Here's what the cross-section looks like. Now, we're interested in the area of this cross-section. And when we talked about the area of the cross-section before, when it was truly a solid for that cylinder, it was just the area of a circle. You remember, it was the area of the circle times the height is what we started with, and then it was the area of this circular surface times a certain width, and so on as we developed the situation. But here, the area is the area of this washer. And we can really think of the calculation of the area as being the area of the big circle minus the area of the little circle. And let's see where that takes us. So the area of the surface of this washer is the area of the big circle minus the area of the little circle. Each of these is some pi r squared amount. The pi can be factored out, so we have big R squared minus little r squared. And the way that it manifests itself in the notation is like this. It's pi, then we have our interval, and we have this big radius associated with an x squared, and the little radius associated with an x squared. And we want the difference between those two because of that situation up there. All right, here's a problem that uses this kind of technique. And this situation occurs anytime you have a piece of the figure that's kind of dug out, you see. You're going to get this washer effect. And here it is. Here's the figure, but let's read the problem.